This is the video record for probability and stochastic process course homework 10, and this is the video for question 1. The question asks us to collect the definitions and the simple probabilities of the examples of the following stochastic processes. The properties could include the probability masses or density, the mean, the autocorrelation, and the autocovariance functions of the stochastic processes. The first is to find the Poisson process, and as we know, the definition of the Poisson process is when the number of m, the number of points is number is n, point ti is in the interval from t1 to t2, and the length or the magnitude of the interval is t equal to t2 minus t1. Then this is a Poisson process, random variable of t, and it has a parameter of lambda t, where we can find the probability of the stochastic process to be p of n equal to k is equal to e to the degree of lambda t times lambda t to the degree of k over k exclamation mark. And also it has the property that if T1 to T2 and T3 T4 are non-overlapping, then the random variables n and n1 and n2, which are the number of different t's in two different intervals, they are relatively independent. And the third property is there is no more than one Poisson point at a moment t. It means that there can be only at most one Poisson point at a moment t, or at a time t. And the first order probability masses of this Poisson process is p equal to xt equal to k is equal to e to the degree of minus lambda t times lambda t to the degree of k over k exclamation mark, and the mean is exactly lambda t. Its autocorrelation is r t1 t2 equal to lambda squared t1 t2 plus lambda minimum of t1 and t2. Its autocovariance is c t1 t2 equal to lambda squared t1 t2 plus lambda minimum of t1 and t2 minus lambda t1 times lambda t2, and it should be equal to lambda times the minimum of t1 on t2. And the Poisson, the second thing is the Poisson increment process, and the definition of the Poisson increment process is yt equal to xt t plus epsilon minus x of t over epsilon, where epsilon is like a very small number and where xt is a Poisson process. It has the first order probability masses equal to p yt equal to n over 6 epsilon is equal to e to the degree of lambda epsilon and times lambda epsilon to the degree of n over n exclamation mark. It has the mean equal to lambda. Its autocorrelation is equal to r t1 and t2, and we can see it's divided into two different situations, where the first is lambda square, and the second is lambda square plus lambda over epsilon minus lambda times t1 minus t2 absolute value over epsilon square. And these are dependent on the actual value, or the absolute value of t1 minus t2, whether it's larger or equal to epsilon, or it's less than epsilon. And its autocovariance also has two different situations, where the first c t1 and t2 is equal to 0 when t1 minus t2 take absolute value of that is larger than or equal to epsilon. And the second thing, when it's the otherwise situation, the c t1 t2 is equal to lambda over epsilon minus lambda times t1 and minus t2 take absolute value over epsilon square. And the third thing is the Poisson impulse process. As the name suggests, the Poisson impulse process is actually the to take derivative of the Poisson process over t, so it's equal to z of t equal to dx of t over dt, where xt is a Poisson process, and it doesn't have a probability masses. I couldn't find it anywhere in the textbook, and there it has the mean of lambda. Its autocorrelation is a lambda squared plus lambda sigma of t1 minus t2, and its autocovariance is c t1 and t2 equal to lambda times sigma of t1 minus t2. And the fourth question is the semi-random telegraph signal. It is defined like this, where x of t is also defined as a Poisson point, but the probability of that is defined by p of nt1 t2 equal to k is equal to e to the degree of minus lambda t times lambda t to the degree of k over k exclamation mark, and x of t is equal to 1 when k is even in 0 t, and x of t is equal to minus 1 where k is odd in 0 t. And the probabilities of that is when the first order probability masses is written as here, and it is divided into two different situations where x of t is equal to 1 and x of t is equal to minus 1. It has a mean equal to e to the degree of minus 2 lambda t. Its autocorrelation and autocovariance are also listed here. And the fifth problem is to find the random telegraph signal, where we also define x of t to be a Poisson process, and the random telegraph signal is y of t is equal to a times x of t, and its probability is equal to p of a equal to 1 and p a equal to minus 1. They are both 1 over 2. I'm sorry, x of t is a semi-random telegram signal, and it has the properties where its probability mass is equal to 1 over 2, and its mean is equal to 0. Its autocorrelation is equal to e to the degree of minus 2 lambda times t1 minus t2, and the autocovariance of that is also equal to the same value. And the sixth question is a random walk, and the random walk is when we toss a fair coin n times, and the k is the number of heads in n tosses. So the x of nt is equal to ks minus m minus k times s, which is exactly 2k minus n when we take a product with s. And its properties are here. The first order probability masses is actually equal to p equal to this is like a matrix and n plus r over 2 times 1 over 2 to the degree of m. Its means is equal to 0, and its autocorrelation and autocovariance are equal to the minimum value of n or m times s squared. The seventh is Wiener process, and the Wiener process is w of t, where we define it as a limit of x of t when at capital T is approaching 0, s squared over t is approaching alpha, and n is approaching infinity. And also x of t is a random walk in this equation, and it has the properties here. F of its first order density function is f of wt equal to 1 over the root of 2 pi alpha t times the e to the degree of omega of w squared over 2 alpha t, and its means is equal to 0. Its autocorrelation and autocovariance are both the minimum value of t1 and t2 times alpha. And this is the end of this video record.